Welcome to the Deep Dive. Today, we're diving into something really cool. I think the connection between electricity and magnetism.
Yeah, always fascinating stuff.
It is. It's going to be electrifying. Haha. Okay, so I guess let's start with magnets, right? Everyone's played with magnets, I think. We all know that they have that pull. But what exactly is that pull?
Well, we call it a magnetic field, and it's basically a region around a magnet where magnetic forces act.
Okay.
So it's like an invisible aura.
Interesting. So it's not just the magnet itself, it's like a whole area around it.
Exactly. And to help us understand this field, we use this idea of magnetic field lines.
Yeah.
You can imagine these as invisible tracks showing the direction and strength of the magnetic force. So if the lines are crowded together, that means the field is stronger, and if they're spaced out, the field is weaker.
I see. So how can we actually see these lines?
Yeah.
Because they're invisible, right?
Right. Well, that's where things like iron filings and a compass come in. If you sprinkle iron filings around a magnet, they align themselves along these invisible field lines.
Right.
So you actually get to see this visual representation of the field.
Yeah, I remember doing that in school. It's like magic.
Yeah.
So speaking of compasses, how do those work with magnetic fields?
Well, a compass needle is basically a tiny magnet itself.
Okay.
And it aligns itself with the Earth's magnetic field, which is why it always points north.
Gotcha.
So it's kind of like a little explorer always following these invisible magnetic lines.
I like that. So it's basically like the compass needle is feeling the Earth's magnetic field.
Exactly. And if you bring a compass near, say, a bar magnet, you'll see the needle actually deflect, showing you how those fields are interacting.
That's cool. Okay, so now I want to talk about this connection between electricity and magnetism.
Yes.
I've heard about it, but never really understood how it works.
Well, it all started back in the 19th century with a scientist named Hans Christian Ørsted. He was doing an experiment with a compass and an electric current when he noticed something really groundbreaking.
What was that?
Well, as he passed the current through a wire, the compass needle nearby moved.
Oh, wow. So just by passing electricity through a wire, it made the compass needle react.
Yeah. It was a simple observation, but it led to this big understanding that an electric current flowing through a wire creates a magnetic field around it.
That's pretty amazing.
And this connection between electricity and magnetism is what we call electromagnetism.
Okay.
One of the fundamental forces of nature.
So by running electricity through a wire, we basically create a magnetic field. That's pretty wild.
It is wild.
What does this magnetic field around the wire actually look like?
So picture this, the magnetic field lines form these concentric circles around the wire.
Like rings.
Yeah, exactly.
Okay.
And to figure out the direction of those field lines, we can use this handy trick called the right-hand rule.
Right-hand rule. Okay, I'm intrigued.
So imagine you're holding the wire in your right hand with your thumb pointing in the direction of the current flow.
Okay.
The way your fingers curl around the wire shows you the direction of those magnetic field lines.
Oh, that's cool. So if the current's flowing upwards, my fingers would curl around clockwise.
You got it.
Okay, cool.
Right.
So the strength of this magnetic field, it's not like uniform everywhere, right?
Right. Depends on two things: the magnitude of the current and the distance from the wire.
That makes sense.
Yeah. So the stronger the current and the closer you are to the wire, the stronger the magnetic field will be.
Okay, so we've been talking about straight wires. What happens to the magnetic field if we bend the wire?
Good question. Let's imagine bending the wire into a circular loop.
All right.
What happens is the magnetic field lines at the center of that loop actually become straight lines.
Oh, wow.
So you get this concentrated magnetic force right in the middle.
So the shape, like, focuses the magnetic force.
Exactly. And
Right.
each segment of the loop is contributing to that stronger force at the center.
Interesting. So what if we have multiple loops of wire?
Then we get into what's called a solenoid.
A solenoid.
Yeah. It's
Yeah.
basically a tightly wound coil of wire that forms a cylindrical shape.
Okay, I'm picturing it.
When a current flows through it, it becomes like a super-powered magnet.
A superpowered magnet. How does that work?
Well, each loop in the solenoid is contributing to the magnetic field.
Uh-huh.
So with all those loops packed together, the field strength gets multiplied,
Oh, I see.
creating a much stronger and more uniform magnetic field inside the solenoid.
So it's like taking those straight lines from the center of a single loop and kind of like extending them throughout the whole coil.
Exactly. Inside the solenoid, the magnetic field lines are nearly straight and parallel,
Wow.
showing you that uniform field. And then outside the solenoid, the field pattern actually resembles that of a simple bar magnet.
That's pretty cool.
Yeah.
So are solenoids basically like electromagnets then?
You could think of it that way, yeah.
Yeah.
And these solenoids are used in so many things. doorbells, speakers,
Wow.
even medical imaging equipment like MRI machines.
That's amazing. So
Yeah.
just by like coiling a wire and passing a current through it,
Right.
we can create these powerful magnetic fields that are used in all sorts of technology.
Absolutely.
Now, I have a question about forces. We know that a current-carrying wire creates a magnetic field.
Yes.
But can a magnetic field also exert a force on a current-carrying wire?
Yes. Think of it as like a two-way street.
Okay.
Electric currents create magnetic fields,
Mm-hmm.
and those fields can then act on electric currents.
So they kind of work together.
Exactly. And
True.
to figure out the direction of the force on that wire, we use another handy rule called Fleming's left-hand rule.
Okay, another hand rule. I like it. Tell me with this one.
So this time you stretch out your thumb, forefinger, and middle finger of your left hand, so they're all perpendicular to each other.
Okay.
Your forefinger represents the direction of the magnetic field.
Mm-hmm.
Your middle finger points in the direction of the current.
Okay.
And your thumb will then point in the direction of the force acting on the wire.
So it's like each finger represents one of those key players.
Exactly.
Magnetic field, current, and force.
Yep. And Fleming's left-hand rule is really helpful to understand how electric motors work.
All right.
Because they essentially convert electrical energy into mechanical energy by harnessing this force between magnetic fields and current-carrying conductors.
This is all starting to make sense now.
Good.
So every time I use an electric motor, I'm seeing this interplay of forces in action.
You got it.
That's pretty cool. So we've covered a lot here. I think it's time for a little pause and reflect.
Yeah.
What are some of your initial thoughts on all this?
I mean, it's just amazing how these seemingly invisible forces
Right.
really shape our world in such profound ways.
I agree. And what about you? Any aha moments?
I think for me, it's realizing that these forces are at play in so many aspects of our lives, from a simple compass to something as sophisticated as an MRI machine.
Right. We often take these things for granted,
Yeah.
but it's really this invisible world of electricity and magnetism working behind the scenes to power our everyday lives. And we're just getting started. I think there's a lot more to explore here.
Absolutely. Yeah, there's so much more to uncover.
There is. Now, I'm curious about something. We were talking about how solenoids act like a bar magnet. Can we actually create a magnet using electricity?
Yeah, that's the cool thing. We absolutely can. And that's where this idea of an electromagnet comes into play.
Okay.
Remember those super-powered magnets we talked about, solenoids?
Yeah, those tightly wound coils of wire.
Exactly. If we take a solenoid and put a piece of soft iron, like an iron nail, right in the center of that coil,
Okay.
and then we pass an electric current through it, something really amazing happens.
I bet the nail becomes magnetic.
You got it. The magnetic field from the solenoid actually magnetizes that iron core.
Oh, wow.
And here's the cool part. That iron core actually enhances the magnetic field, making the electromagnet even stronger than a solenoid by itself.
So it's like the solenoid gives the iron this magnetic superpower.
Uh-huh. Yeah, I like that. And the really neat thing about electromagnets is that we have control over their magnetism.
Control. What do you mean?
We can turn the magnetism on and off just by controlling that electric current.
Oh, wow.
So when the current's flowing, it's a magnet, switch it off, and poof, the magnetism disappears.
That's incredible. So it's like a switchable magnet.
Exactly. And we can even fine-tune the strength
Really?
by increasing the current flowing through the coil, or by adding more turns of wire to the coil, we can make a stronger electromagnet.
So it's like having a magnet on demand.
That's a good way to put it.
That's really cool. Where do we actually use these electromagnets in the real world?
Oh, they're everywhere. Think about those giant scrapyard cranes that pick up and move heavy metal objects.
Oh, yeah?
They use powerful electromagnets or loudspeakers. They use electromagnets to convert electrical signals into sound waves, or even some high-speed trains
Wow.
use magnetic levitation to float above the tracks using electromagnets.
That's so cool. So they're really versatile.
Very versatile,
Yeah.
yeah.
Now I want to shift gears a little bit and talk about safety.
Okay.
We're dealing with electricity and powerful forces here.
Right.
What kind of precautions do we need to take when we're working with electric circuits, especially in our homes?
Yeah, that's a crucial point. Safety should always be our top priority. So our homes are powered by what we call alternating current, or AC electricity.
Right, AC electricity, and that's different from direct current DC,
Yeah.
right? Like what batteries use.
Exactly. AC electricity is the standard for powering our homes, and it typically comes in at around 120 volts here in the US,
Okay.
or 220 volts in many other parts of the world.
Gotcha.
And it alternates at a frequency of 50 or 60 hertz, depending on where you are.
Okay, 120 volts sounds pretty intense. What happens if we accidentally touch a live wire?
That's a great question, and it highlights why safety features in our homes are so important.
Mm-hmm.
So in a typical household wiring system, you have 3 wires.
Okay.
You have a live wire, a neutral wire, and a ground wire.
Right, and I've seen those different colored wires in, like, electrical appliances. What do they each do?
So the live wire carries the incoming electrical current, and it's typically covered in black or red insulation.
Okay.
Then you have the neutral wire, which completes the circuit, carrying the current back to the source, and that's usually white or gray.
Okay. And what about the ground wire? I know it's green, but what's its purpose?
The ground wire is like our safety net.
Okay.
It's connected to a metal rod driven into the ground, and it provides this path of least resistance for any stray currents to flow safely into the earth if there's a fault.
Oh, so if there's like a short circuit or a problem in an appliance, the current will go through the ground wire instead of through us.
Exactly. It prevents electric shocks and keeps us safe when using appliances.
So that's why it's so important to have things properly grounded.
Absolutely. It's like having a safety valve for electricity.
That makes a lot of sense.
Yeah.
Is there anything else we need to be careful of in our home electrical circuits?
Yeah, absolutely. One of the biggest concerns is overloading circuits.
Overloading, what does that mean?
So it happens when we connect too many appliances to a single socket, or when the electrical demand is just more than the circuit can handle.
Okay.
Imagine like a highway with way too many cars trying to squeeze through it can lead to some dangerous situations.
So how do we prevent overloading a circuit?
Well, being mindful of the power ratings of our appliances is key.
Well.
Each electrical circuit in our home has a specific current rating, typically 15 or 20 amps. And we need to make sure that the total current draw from all the appliances plugged into that circuit doesn't exceed that rating.
Right, so if we overload it, that can cause all sorts of problems.
Absolutely. It can lead to too much current flowing, which can overheat the wires,
Uh-oh.
potentially causing them to melt or even start a fire.
Yikes, that's scary.
Yeah.
What are some signs that a circuit might be overloaded?
So if you notice that lights are dimming, especially when you turn on another appliance, that's a sign.
Okay.
Or if you feel an outlet or switch plate that's warm to the touch, that's another red flag. And if you ever smell burning plastic or see sparks coming from an outlet,
Okay.
you need to disconnect the power immediately and call an electrician.
Right. Safety first. Now, I know that fuses and circuit breakers are designed to protect us from these kinds of dangers. How do they work?
So fuses and circuit breakers are basically safety valves for our electrical circuits.
Okay.
They're designed to interrupt the flow of electricity if the current goes beyond a safe level.
So they're like electrical bodyguards.
That's a good way to think about it.
Cool.
So a fuse is a small device with a thin wire inside that melts and breaks the circuit if the current gets too high.
Oh, okay.
Once it blows, you need to replace it with a new one with the same amperage rating.
And what about circuit breakers?
Circuit breakers are more modern and reusable.
Okay.
They work by tripping a switch when the current exceeds that safe level, basically interrupting the electricity flow.
Okay.
And you can simply reset them by flipping the switch back on.
So they're like resettable fuses.
Exactly. Both fuses and circuit breakers play this super important role in protecting our homes from electrical hazards.
This is all making me much more aware of like the electrical systems in my own home.
Yeah, it's good to be aware.
It's fascinating to think about this invisible world of electricity and magnetism at work all around us. But it's definitely important to understand the safety aspects as well.
I agree. Understanding how these forces work and how to use electricity safely is really empowering.
Right.
Allows us to enjoy all the benefits of modern technology without putting ourselves at risk.
Absolutely. This has been such an insightful deep dive so far.
Yeah, it has.
We've covered the fundamentals of magnetic fields, explored this connection between electricity and magnetism, learned about electromagnets, how they're used, and even delved into the importance of electrical safety.
It's amazing to think we've only scratched the surface.
I know, right? But there's still so much more to explore. Let's continue this electrifying journey as we uncover even more fascinating secrets of the electromagnetic world. All right, so we've covered a ton of ground already, from those basic magnetic fields to how to stay safe with electricity at home.
It's been quite a journey.
It has. But, you know, my mind is still buzzing with questions.
I bet.
One thing I've been wondering about is we talked about how electric currents create magnetic fields.
Right.
But is it possible to go the other way? Can we use magnetic fields to create electricity?
You're thinking about electromagnetic induction, one of the most fundamental principles in electromagnetism.
Electromagnetic induction, that sounds pretty sci-fi to me.
It does sound a little fancy, but it's actually much more down to earth.
Okay, good to know.
It's basically the process of generating an electric current in a conductor, simply by moving it through a magnetic field or by changing the magnetic field around the conductor.
Wait, are you saying that just by moving a magnet near a wire, we can create electricity?
You got it. It's this amazing interplay of forces.
That's wild.
It really is. This was actually discovered by Michael Faraday back in the 19th century.
Okay.
And it totally changed how we generate and use electricity.
So how does it actually work? What's the secret sauce behind this electromagnetic induction thing?
Well, it all comes down to moving charges and how they interact with magnetic fields.
Okay.
So when a conductor like a wire moves through a magnetic field, the electrons in that wire experience a force that pushes them in a specific direction. And this movement of electrons, that's what we call an electric current.
So the magnetic field is kind of giving those electrons a little nudge to get them flowing.
That's a good way to visualize it. And the faster the conductor moves through the field, or the stronger that magnetic field is, the greater the induced current will be.
Okay, so are you telling me that all those giant power plants that give us electricity are basically using huge magnets and moving wires to generate power?
Haha, you're catching on quickly. That's the fundamental principle behind most electrical generators. Wow.
They use different ways to move conductors through magnetic fields, converting that mechanical energy into electrical energy.
It's amazing to think that this invisible force is basically powering our whole world. Now, I'm curious about those hand rules we talked about earlier.
Yeah.
Do they apply to this electromagnetic induction as well?
Another great question. Yes, we do have a hand rule for this, but this time it's Fleming's right-hand rule.
Right-hand rule. Okay, got it.
And this one's specifically for electromagnetic induction.
Okay, so how is this different from the left-hand one?
It's pretty similar, but instead of using your left hand, you use your right hand.
Okay.
Extend it out with your thumb, forefinger, and middle finger all perpendicular to each other.
All right, right-hand fingers out. What do they represent this time?
So your thumb, this time, indicates the direction of the motion of the conductor.
Okay.
Your forefinger points in the direction of the magnetic field. And your middle finger will point in the direction of the induced current. So we basically just swap the roles of the middle finger and thumb from the left-hand rule. Current becomes motion, and motion becomes current.
You got it. And this rule helps us figure out the direction of the induced current in all kinds of scenarios.
This is really starting to click for me now. We could use Fleming's right-hand rule to figure out how to generate electricity.
Exactly.
Just by moving magnets and wires in specific ways.
It's this fundamental principle behind so many things, from power generation to electric motors, transformers, and even wireless charging.
That's incredible. This whole deep dive has been amazing.
It has been fun.
We've explored those magnetic fields, the connection between electricity and magnetism, the magic of electromagnets, and even how these forces are working all around us in our everyday lives.
Absolutely. It's a whole new world we've uncovered.
It really is.
Yeah.
What are some of your final takeaways from all of this?
Well, I think the biggest one is that electricity and magnetism aren't these separate things.
Right.
They're two sides of the same coin, this amazing force called electromagnetism.
It is amazing.
And it's shaping our world in ways we're only starting to understand.
I agree. I hope everyone listening will take a moment to think about these invisible forces at play next time they use an electronic device.
Me too. It's the interplay of electricity and magnetism that really makes so much of our modern world possible.
Absolutely. Thanks for joining me on this electrifying journey.
It was my pleasure.
Until next time on The Deep Dive, keep exploring and never stop asking questions.